challenge because with every with each approach, we have like different tasks and different you know um, thing that we need to do in order to meet the target.
So thank you so much.
How do I set it up? I don't know. Okay. Oh, cool. Hi everyone, I'm working on the push staking protocol. The push notifications protocol, and it's one of our sponsors projects. I believe there's someone from the push team here right now. Is there? No, they didn't come. Okay, so for those who don't know, what's push? Basically, it's a Web3 native communication protocol enabling cross-chain notifications and messaging for dApps, wallets, and services. So notifications can be sent to the users of the dApps from the dApps via web, mobile, or Web3 providers. And how it works is that the dApp owners are called channel owners, and they can send mass unencrypted information to all the users in their app or encrypted messages to specific users. So basically, the component that I'm focused on is the staking component of it, and it's all the functionality lives in PushCore v2, which is an upgradable smart contract. And I'm going to break it down to you because that's the main touch point that I'm going to manipulate. I'm going to read from my diagram. So so basically, PushCore v2 is upgradable, and it includes lots of different logic flows. So it includes channel management, creation, updating, activating, deactivating of channels, notification management. It also, these two facets produce protocol fees, and then the protocol fees, part of them are contributed to staking logic. So basically, users who hold push tokens can stake in this protocol. And so, in this contract. And so this contract also includes staking, unstaking, reward distribution, calculations, as well as epoch initialization. And epochs are important to understand here with the building of the next version of staking for push. I just want to point out that this contract, because it's upgradable, it's the implementation contract. So it saves the patterns of state storage in it, which come from it's inherited from two external contracts. And then, like I said, protocol fees are used to fund staking rewards for token holders right now. And it also has a governance component where governance verifies or blocks channels, and it controls the fee structure of how much these channel flows generate for the protocol. So basically, as a user, you interact with the proxy contract. The proxy contract stores its own state. It performs a delegate call on behalf of the user, and then the delegate call invokes these different functionalities in the context of this state. And so basically, whenever this is invoked, state is updated, and then it goes back here. The transaction updates the state and the proxy. So this is how currently push v2 works. And so for the push v3, the goal is to split out staking to its own separate protocol and remove it from push core. So push core would be focused on channel management and notifications and collecting fees, as well as saving the state pattern definitions. But all the staking logic would move to its own designated contract. So basically, how the split is going to work is that the push core will be updated to v3, and it would stay the implementation protocol, and it would interact with a proxy just like we saw on the other slide. All that stays the same. One thing I didn't mention is that staking also is now going to incorporate not just token holders, but also integrators. So different projects that are going to integrate with Push, they're going to integrate their wallet addresses with Push Core v3, and hence they will also be considered stakers for in this new iteration of the protocol. So it's basically splitting out staking into its own designated contract where staking is not upgradable, and the upgradable code remains in here. And so still, protocol fees contribute to the staking rewards. And so the staking rewards now will go to token holders as well as token integrators. So how is this? How are these funds going to go there for rewards? I'll tell you in the next slide. But so the most important things to think about here is that there's two entities for staking: token holders as well as integrator wallets. And regarding the integrator wallets, basically governance adds and removes them. And these actions, so when governance adds a staker, that means it's as though, adds a wallet integrator. That means it's like the wallet integrator, they staked. And when governance remove them, they unstaked, basically. Yeah, so usually in staking, or in this context, every epoch of staking is initialized. In Push, each epoch is 21 days. And so every time there's a new epoch initialization, the rewards for that epoch are set in the contract based on user actions, new stakers, new unstakers, people who have claimed their rewards, etc. And so basically, how I'm going to build it is that when an epoch initialization occurs, okay, now I see a problem with my solution, because I was saying like every time an epoch initialization, actually no, it's correct, sorry. Every time, so the staking contract is what's going to do the epoch initialization, and within that initialization call, it will pull rewards from Push Core v3, because Push Core v3 will still have this protocol pool fee. So the protocol itself is also a pool, and so with this pull transaction, funds will be funneled into the staking contract, and in the staking contract, there's going to be two rewards pools. One is the wallet fee pool, and one is the holder fee pool, and those can be designated with different percentages of who gets how much. Did I say that? Okay. And so the implications of this is that Push Core, so Push Core right now, it holds the stake for staking, but since staking is being split out, the a migration of state is going to have to occur. Yeah, and basically that's it. That's what I'm going to be working on. So I took the last week to break down how staking works and how rewards are calculated and like all these things in Push. And my goal is next week to build the staking contract as well as write tests for it. And then the final goal towards the end is having also docs for it and doing a testnet deployment.
Do you work at Push Protocol?
No, it was one of the projects that were presented to us to work on. So since I like to work with Solidity. I just decided to do that.
In the design, you said that the integrators will get some fee. Integrators will get some fee from staking.
Yeah, some rewards, because the integrators will now be considered stakers.
But isn't that too easy to game? Like I can be a fake integrator and I just start collecting fee because there's no cost to use the protocol as of now.
Possibly, but integrators are added and removed via governance. So if there's an active governance community for push, then it's hard to game that because the community would be like, no, this person doesn't deserve to be part of this.
Actually, regarding the governance, why do they need to verify or block the channels themselves? Why this has to be custodied? Do you have?
That's how the protocol is currently now. I don't know why they do that.
It's also because of spam sometimes, because people start using the channels and DDoSing it. So you need some way to stop it.
It's social stimuli, right? Token utility. Like how do you know that that's the actual Uniswap announcement chain?
It happens with status too. Like people start spamming the system. So you need somehow to stop
But
it.
they pay the gas, right?
No, there's no gas because the tokens, like it's a different network, so it's almost free.
Almost.
Yes, but if somebody has like push tokens, then it's free for them. Because when you integrate with them, like they give you a huge chunk of money just to integrate, and then you can start spamming the system.
Yeah, but like it's just like on-chain things. You can like if you don't want to see them, you can just filter the interface.
Oh, yes.
Why do you have to do that on like smart contract level? Like it's,
Okay. Thank you.
Okay, so voice key. Voice key.
it's like the centralized system and want to let people spam like it's just like
I know Intel used to do that. It's not completely easy. There are many ways, and it's a whole lot of work. But the bundle is very high, and we didn't get there's no gas. So it's not technically a transaction. It is just a broadcast. That's why it can be DDoS. That's why you need to somehow stop the channels.
as I understand right now that the messaging goes through the blockchain.
No, messaging is on their own authentication.
So they like widely channel this like on the chain and then they are passing the transaction.
Collecting fee on the chain. The messages are not on the chain.
I guess I should use this right here. Okay, hey everyone. Okay, so we have outlined the problem a little more, and we know that our problem, or that we're trying to solve right now, is just biometrics training takes place on big tech servers, right? And we want to avoid this. So we are introducing VoiceK, which is a private CK voice print computing and authentication. And here's the team. Here's us. We have been recently joined by Fi and Lucila. And yes, we are bringing this to the world, right? So for this week, we have just been outlining the specifications and just creating some diagrams for us to understand and for us to show the public, right? So this user interaction diagram contains just the basic interaction with our application. We are trying users, or a normal person, uses an app to register, right, on a service. And then he becomes a user, and then the user can do voice training and authentication with other application services. And the DID is going to be like identification generator for us, based on our voice print. We have another diagram here. This is like kind of a component diagram. We have a biometric auth app, which is here. This is going to be a web app. that's going to contain all these little modules. We have a decentralized ID system over here and a service app system over here. Our web app is going to record the voice of the user, which is going to go here, voice capture. Then voice pre-processing functions are going to take place. Then there's going to be a voice analyzer, and this is going to be sent to an encrypted storage. Then this is going to a prover using CKML and an ID manager as well. And this is going to go to be stored in a decentralized ID system. And the proof with the ID is going to go to a service or a third-party service application to authenticate the user, basically. Yes, we created our Notion. We have our tasks, right? And if you remember last time we presented, we said we were going to use P256. But since this is a thing that just calls libraries that use Google services and Microsoft services, we are not going to use this anymore. Or if we plan to integrate to this, we will add another option that doesn't call these libraries and just uses web authentication methods primarily, right? We did a little mock-up as well on the app with the help of Phi, and just this mock-up is like the mobile application. It's just going to be a simple button that's going to record our voice. It's going to ask voice recordings like 5 or 10 times so that we can train a voice model after, right? Just a simple application. We also did some coding for this. We have an application. The application asks for permission to record the voice. I know this is very shady, but users are going to have to trust the front-end code for this. And yes, so then it starts recording, and all these recordings are going to go into our model, which we're going to explain right now. Diagram first or this first? So this is kind of like the full process, right? The user inputs a raw voice with the microphone, and then there's the audio capture and pre-processing. There's the feature extraction, where we do a normalization, silence removal, free emphasis filter. No CK around here yet. Then we do a feature vectorization, which we convert the waves into a fixed length vector. And then there comes the CK part. We are going to use CKML with eCKL, which is a protocol that we found, to train this NN model on the feature vectors. And then eCKL allows recreating a prover and verifier for the trained model. With this, we can generate our voice print already, and we're going to have this voice print generation here using the trained model. This model is going to be trained with our voice, and then it's going to generate the voice print, right? It's going to generate a unique voice print for the user. Then we're moving on to storage, right? We're going to divide the voice print into shares using a secret sharing scheme. Then we're going to distribute and store these shares securely across multiple independent nodes so that no single node has the full access to the voice print, right? Here's a little diagram of MPC. If you know MPC or a little familiar with it, you can see that it takes place on a number of nodes. And yeah, so here's like a division, right? This is the registering process for a user. And then there's the authentication process where a user is already registered and he wants to authenticate, right? And this is going to be using one of the sponsors, which is CKM. And how it's going to be used is just when the authentication is required, we're going to capture and process a new voice sample, same as we did first time. And then we're going to use MPC to perform calculations on the stored shares without reconstructing the full voice print. Then we're going to send this to CKM to compare the new voice print with the result from MPC. And what CKM allows us to do is just allow this comparison to be done privately and verifiably. They're going to send the CK proof that the computation was done correctly, and they're not going to send any information about the voice. And then it comes the verification part, which is going to take place on the third-party services, right? This is going to be, we plan to do like an API or something that services can connect to and just run the verification step for the proof that CKM is going to send to the service. So CKM generates a proof, and the comparison was performed correctly, and this proof can be verified on any compatible blockchain without revealing the voice prints. So yeah, that's everything that we've worked so far. Thank you. Yeah, we already did some coding, of course. We have our Jupyter notebook here, which is taking the pre-processing of the voice already. So you can see some cool graphics over there. And of course, we have our code for this little application that we're making. We are capturing the voice already, but we don't know what's going on, so we have to debug these transactions to save the audio to the devices. Here, sorry. Thank you. Yes.
What's the math they're using to anonymize the voice? Like, how are you looking at the waves, or what's the process basically?
Sorry, can you repeat? I didn't hear you.
How are you anonymizing the voice? It's like
Analyzing, okay. Normalizing, anonymizing. Okay, we are using the ECKL, that is a framework that do all the anonymization for the ML neural network process. So we are doing the training with that, and from the training we got the TensorFlow model and sent to this framework, and it give us the circuit and the CK keys for verification of the computation we have done. Yes, and all of that part is done in the user device. So basically, it is not being leaked on that stage. Yes.
Yeah, the part we will share with another service or application is just a proof. Then we don't share any other data about a voice print or something like that. But it is verifiable using the secret artifact that we will provide to the verifier systems that want to implement these authentication services.
So you guys are sending the voice to the ECKL AI model, but that voice message is also private because it's a CKL.
Yes.
Yes.
And you just get the model back,
Yes.
and you just run it off.
Yeah. We're also thinking on like adding a layer for AI verification, for verify that the voice is not AI generated, but we are thinking on that later. Yes. Yeah. But basically, it's another neural network that do that. So yeah, that's it.
What happens on the private authentication step? The one that you use here, of course, they say you're authenticating it against the private shared identity, but also it's verifiable. So is it like personal?
CKM, it's like a CKVM. And if I understand correctly, it's like they have their own servers, and you can just be sure that they are doing the computation with the trained model that we already installed, let's say, and they are getting back just a CK proof of the calculation that it was correct. So for us, it will be a CK proof that the user is indeed the one that's sending like the voice. I don't know.
One of the inputs is the, as far as I understand, privately shared voice prints that you never recover because it's a PC, right?
Yes, yes,
So
that's
does that goes to the CKM servers?
yes, yes,
And like secret shared state.
yes. It should go in a secret share state. Yeah,
So
yeah.
that is like there is a part of that is a PC, but then on a single server that sort of finishes, but it is like secret shared data. You kind of struggle to see what's the method there. So it's like there is a model that is run on the ZK.
Oh, the
MIPS,
CK
server
MIPS CKM server.
that compares it to some secret shared data.
Yes.
The user's voice also secret shared in the same way.
I'm not really sure how we're gonna send that voice. I don't know if you have an idea already of that.
We're thinking about that. Haven't resolved yet.
Yeah, I guess we'll have to figure it out as well.
Yeah.
Yes, yes, yes.
Because at the end of the day,
Yeah, thank you.
Thank you.
Thank you.
In your diagram, it showed that the model is trained inside the mobile, right?
Here.
It's trained inside the mobile.
We're planning to use it an pre-trained model, just installing the pre-trained model and then using that to train with the inputs, the voices. Yes, it should be.
To update the weight.
Yeah, to update the weights of the model. Yes, we plan on doing that. And if it's not possible, we can move this training as well to CKM. Yeah.
But how would you guarantee the quality
Of the training.
data?
I'm not sure about that. You know that? You know?
How would you guarantee the quality of the voice? The voice.
Sorry, can you repeat?
Can you?
How can you guarantee
Oh, yeah.
the quality of the voice of the input data that you put into the model to train?
He's asking how can you guarantee the quality of the voice?
Yes, yes.
Well, for that is because we are doing these steps that basically are adjusting different high levels of frequency, of voice frequency. So we'll first normalize, then remove silence, and yes, basically we do this pre-processing to guarantee that the voice is correctly, in some ranges.
But if someone want to like sabotage your app and they don't put that
They don't put that voice. So if someone wants to I guess corrupt the model, that's what you're asking, and they just send like random data or something like this.
Okay.
How can we be prepared for that?
We're not sure, but we have to think about it.
Another case is that how can you guarantee that your model is not overfit? Like when you train with a specific type of data, it's too much.
Oh yeah, the overfitting. Yeah, the
Oh,
overfitting
yeah.
part. How can we not overfit the model?
Well, we do that here in the model training. Maybe, but basically, the normal part of ML, we use scores and things like that to treat overfitting. So the simple part of the ML, the thing that we do in ML models, yes.
It's very hard because there's no way we can investigate the data.
Yes, you're right.
Yeah, but we do that here in the model training. Yes, we take care of that with scores and errors. Yes.
Thank you.
Okay.
Commodity?
Hello everyone, I'm Box and I make a small tour about Jupyter notebook. Sweet. Okay. About Jupyter notebook for Solidity. Yeah, that is a very simple tool. And what can it do? So it provides a very easy interface to use it. It's very seems like the Jupyter book. I'm not sure. Did you use the Jupyter book? Yeah, it's the Solidity for Jupyter book. So you can let your code sleep at a multi-fragment and run it step by step. And you can track the stack, track the memory, and